if this works. So in honor of today being national, actually I think an international holiday or intergalactic holiday, so I want to thank the organizers for letting me come to speak on extending the support and optimizing test functions to bound the lowest zero of Cuspidal new forms. So what we'll do today is we'll talk about the correct field to study zeros. We'll discuss the tools and techniques. I'm going to focus for the most part on easier examples rather than the ones that I'm really looking at with students. And then as time permits, I will talk about some future work that I'm doing with some students. What I love about these projects is the background needed for students to get involved is very minimal. And as people who are teaching at primarily undergraduate institutions, if you're looking for projects for students, this is a huge plus. Some of the number theory projects are really not number theory projects. They're projects in functional analysis. The only people who care about the results are number theory, but you can use a lot of the number theory as a black box. There's going to be a lot of slides that I'm not going to discuss. They will be available online. So if you want to see some more of the details, they're there. This is just a plug for the Polymath Junior. It's an online REU program. If anybody is looking to get involved with some students, I always have lots of projects. I'm always looking for more people to do projects with me. If you have some students of yours who are now graduate students who are looking for opportunities to mentor, please have them reach out to me. I can always find something for them to do to help. And again, there'll be lots of links and stuff like this if you ever want to see more details. Okay, so as I mentioned, there's going to be four main parts: figuring out what is the correct object to study. This is not always clear what is the right thing to study. And so sometimes by looking at related problems, that gives us an idea of what to look at and what's the correct scale to look at. The techniques are often a little bit different depending on what you're looking at. Are you looking at something in number theory? Are you looking at something in random matrix theory? But there's a lot of similarities. And so I'm going to try to focus on some of the similarities and show how a lot of the stuff we're doing in classes like linear algebra is already enough to get your hand on a lot of good things. Dirichlet L functions are much simpler to do than the things that I really care about with my students, but this is a 9 a.m. talk. Nobody wants to see massive technical details, or at least if you do, I think you'd get in trouble if you said that with the rest of the audience. So I'm happy to talk afterwards to anybody who wants to see the technical details, but I'm going to focus on the Dirichlet case where things are a lot easier. And then the applications will be trying to bound what's going on near the central point. The bounds will be terrible, but getting better. One of my advisors once described the result of bounding how many zeros are off the critical strip of the zeta function up to a given height as trying to get better and better estimates for the cardinality of the empty set. And so, in terms of the reason, this was Henrik Ivanitz. So in terms of the results we get, they are far from the truth. Some of them are the worst results I've ever proven in my life, where I will prove the probability that something happens is at most 420%. And there's usually faster ways to do that. But the results do get better as you start asking for even more zeros at the central point. And eventually they do become non-trivial. So in the beginning, the results will be bad, but they will get better. And if they don't get better, that's because I only have 45 minutes and not 46. Okay, so the general formulation of what I'm doing is I am looking to understand spacings between events. There's lots of events you can do. It could be waiting lines and banks. And why banks now have just one line that feeds into whichever teller is available next, rather than 4 lines. So there's a lot of interest in studying how long do you have to wait until something interesting happens. We will focus primarily on zeros of L functions. A lot of the subjects began in trying to understand the behavior of heavy nuclei. And so we'll do a little bit of a history lesson. And then from that, very, very difficult to study something like uranium, people started looking at families of matrices. And this became a really good model to understand what was going on for zeros of L functions, which as number theorists, or at least people who are coming to a number theory session at 9 a.m., is something we should all care about. Okay, has everybody seen enough slides on why we care about zeros of L functions that I can skip these? Yes. So we care about zeros, and the more you know about zeros, the more you can say about the distribution of things that you care about. Okay, so there's 3 main parts in all the proofs. There's a slight delay, unfortunately, between when it advances on that and this. I'm going to try to see if I can advance the slides in anticipation. So first of all is finding what is the correct scale to study events. How do things go as we go to the limit? We need to develop some kind of explicit formula relating what we can study to what we want to study. And then the last is those explicit formulas would be absolutely useless if we didn't have a good way to average. So Dirichlet L functions, we will see it's very easy to average. As we start getting to cuspidal new forms, as we start getting to GL3 and higher, it becomes much, much worse. All right, so really brief introduction to physics. If you have 1 point mass in the universe under gravity, life is easy to explain. 2 point masses under gravity, life is still easy to explain. 3 point masses in general configuration, we can no longer write down a closed form expression. So imagine something like uranium with over 200 protons and neutrons and a far more complicated force of interaction. Way beyond anything we can do. So what physicists do is they shoot heavy nuclei into the uranium and see what comes out. And they would love to shoot neutrons of arbitrary energy, but they can't. They can only shoot in certain neutrons. And from that, they get some information of what's going out. It turns out there's an analog of this in studying zeros of L functions. And so quantum mechanics can be reduced to solving the following equation. So H is the Hamiltonian. It describes how things evolve. En is the energy levels, the eigenvalues, and Cn are the energy eigenfunctions. So there are only 2 things that prevent this from being a problem in an introduction to linear algebra. The first is that the matrix is infinite by infinite. And at least at my school, we don't really do infinite by infinite matrices. And the second is we don't know any of the entries of the matrix. And so those 2 things make it a little bit challenging to diagonalize the matrix. And so Wigner's great insight was basically to say, screw that. Let's just take a very large matrix, choose the entries at random, calculate the eigenvalues, and do this again, do this again, do this again, and average over all matrices, and hope that the average behavior describes the typical system. And so he started by looking at analogs from statistical mechanics, from looking at how would you calculate the pressure on the wall. You would need to see which molecules hit the wall in a small amount of time. Each configuration gives you a pressure, and most things will be close to the system average. This is the philosophy of square root cancellation. And this does a phenomenally good job. Frequently, there's some structure in your physical system, and that impacts which matrices you look at. And so we might be looking at real symmetric matrices. So Aij is Aji, and we can define a probability on the matrix by just taking the product of the probabilities of each independent entry. Now, this is how the subject began. As number theorists, we no longer really look at this. We use classical compact groups and Haar measure, and that gives us a nice way of talking about choosing matrix at random. But you can still do something like this. And for students, it's really nice. You can start playing games by putting additional structure on the matrices and see how that impacts the behavior of the eigenvalues. Lots of great avenues for students to get involved. And so to just go through how you would do the calculations, we start off with a point mass, so the Dirac delta functional. So if we integrate f against that, it just returns the value at x naught. And then to each matrix A, we can attach a probability measure by putting a mass of 1 over n at each of the normalized eigenvalues. And so the 2 in the denominator doesn't really mean much. It just allows me to say semicircle later rather than semi-ellipse. The square root of n is what really matters. It's the eigenvalues of an n by n matrix are growing like root n, and we'll see why in a few moments. And so if we want to understand the measure here, if life is good, if we just start calculating the moments of this distribution, so if we just integrate, that would count how many normalized eigenvalues lie in the interval AB. If we calculate the integral of x to the k of that, so it's going to return the kth moment. And if things are nice, if you know the moments, you know the distribution. There's a lot of advanced analysis you need to do, but you can use that as a black box. And the students, if they can just calculate the moments, which has enough good combinatorics, that's enough. So the big result is Wigner's semicircle law. Depending on what conditions you want to do, there's a whole industry as to what is the fewest conditions, what's the weakest conditions you need to assume to get something like this. I'll assume mean 0, variance 1, finite higher moment, so I don't have to worry about the moment generating function existing. Then for almost all matrices, the distribution of its normalized eigenvalues converges to a semicircle. So how do we understand the eigenvalues of the matrices? And these are going to become later in the talk, the zeros of our L functions. Well, one of the most useful results in linear algebra, which students don't appreciate at the time, is the eigenvalue trace lemma. That the trace of the matrix is the sum of the eigenvalues, or the trace of the kth power of the matrix is this sum of the eigenvalues to the kth power. And so now we have a polynomial in terms of the matrix elements. This is essentially the kth moment. All we have to do is divide by n. And so if we can understand these traces, then we know the kth moment. And if we know the kth moment on average, then we should be able to calculate the limiting distribution. So to give you a sense of how useful this is, let's calculate the second moment. So the trace of a squared is the sum of aij, aji. That's aij squared. but because I have mean 0, variance 1, this is really the same as the variance. So on average, each one of these is 1. I have n squared of them. This would be of size n squared. So if we have n eigenvalues, they're all real, and their squares sum to n squared, then each one has to be of size square root of n on average. And so just by looking at the second moment, we now have the right scale to study things. And if you actually want to prove results, then what you do is you just take your matrix, you put in the trace of a to the k, and you do this calculation. And this calculation involves a lot of wonderful combinatorics. And there's a lot of really nice stuff that students can get involved in. You don't need to know that much to do this. You just start playing with structures of the matrices, and you can start to see very interesting behavior. Okay, so now it is time to quickly segue to L functions. Again, I'm going to assume everybody knows all the stuff here, including the fact that the Riemann hypothesis is true. I get at least one paper a week on that. If anybody is interested in refereeing any of these, please let me know. Unfortunately, we do not know that GRH is true. I have yet to receive in my entire professional career one proof of GRH, only proof of Riemann. Okay, I'm assuming everybody is fine with all this. Okay, so, back when Montgomery was a graduate student, I think everybody has heard the story by now, he was talking to the great Freeman Dyson and relating what he saw when he was looking at the pair correlation statistics of zeros of the Riemann zeta function. Just, how often do you have two zeros whose difference lies in a given interval? And Montgomery said to Dyson, this is what I see. And Dyson started, wow, we see something very similar when we look at the distribution of eigenvalues of matrix ensembles. We see something very similar when we look at energy levels of heavy nuclei. And this led to a wonderful dialogue between number theory and physics. The techniques used are very different, but we're seeing something very similar. So when I teach complex analysis, I want my students to get a Pavlovian response. Whenever you see a product, you take a logarithm. Because we are trained to deal with sums. It doesn't matter, but we know how to work with sums. We have much more familiarity. So if you give me something, I'm going to take the logarithmic derivative, and then I'm going to do a contour integral. And if we can write our L function as a product, and this is why when we look at classes of L functions, we always assume we have an Euler product. Well, the derivative of a log is the sum of the derivatives. And then we can just expand this out by using the geometric series formula. And then may the Fourier transform be defined by phi hat of y is the integral of phi of x e to the negative 2 pi I xy. I don't think anybody's going to be following the talk too carefully, but there's lots of different ways of defining the Fourier transform. So it's reasonable to just say once, and it also gives me one more chance to make a Star Wars joke. This will be the last one for today. All right. Once we have this relationship between zeta prime over zeta and the sum, we can now hit both sides with the function, do a contour integral, shift the contour, and on the left-hand side, what we're going to get over here will be taking up things from the zeros and the poles. So if you want to prove the prime number theorem, you integrate against x to the s over s. And then you have this nice indicator function, which will be 1 if p is less than x, it'll be 0 if p is greater than x. But we don't have to do x to the s over s. We could take a more general function phi, and if we put the function phi on the right-hand side, we get phi of s times p to the negative s. Well, we can rewrite the p to the negative s, good, I timed it well, as an exponential. And then you say, that's a Fourier transform. And so this relates over here, when we do the contour integral, we'll get sums over zeros and poles of phi, and on this side, we'll get phi hat. And it'll be weighted by the coefficients of the L function. Since our L function is the zeta function and all the coefficients are 1, you're not really seeing the coefficients there. But if you look at other L functions, you would see that in the explicit formula. So for example, if I do the Riemann zeta function, you get some formula like this, which relates sums over zeros to sums over primes. If I do Dirichlet L functions, which we'll be doing in a little bit with some character chi, you get something similar. The key thing to note with my normalization, my functional equation goes from s to 1 minus s. I have p to the 1/2, then p to the 3/2, etc. Once I hit p to the 3/2, the sum converges. So I only have to really worry about sums over primes and sums over prime squareds. This is where the universality is coming from. It's very similar to the central limit theorem. If I give you any distribution that's nice, I can adjust to have mean 0, I can adjust to have variance 1, and the higher moments only impact the rate of convergence to the Gaussian. It's very similar here. The main term doesn't see the arithmetic of the family that only comes into play when you're looking at these lower order corrections. You could also do things for cuspidal new forms. And again, you get a similar explicit formula, which relates the sum over your zeros to sums of your Fourier coefficients. I'm going to scale the zeros right now. Not a big deal. We'll talk a little bit later as to why we would want to do that. All right, in the interest of time, I'm not going to say too much about all the different statistics people can look at. All I'll say is if you go really high up on the critical line, you see universal behavior. All L functions seem to be behaving the same way. And one of the reasons for this is you have enough to average over. The spacings between zeros get smaller and smaller and smaller the higher up you go. But as number theorists, we often care about what's going on near the central point. If you care about something like the Birch-Swinnerton-Dye conjecture and elliptic curves, it's the central point that contains the interesting behavior. Well, I can't really play many games because what's happening there is happening there. And so we need some different statistics. And so there's a whole slew of results about looking at what's going on high up on the critical line. But all of these statistics are insensitive to finitely many zeros at the central point. So if you throw away a couple of zeros, it's not going to change anything. Well, if we care about what's going on, like Birch-Swinnerton-Dye, throwing away zeros at the central point matters. So you need a new statistic. And this goes back to trying to find what's the right thing to study. And so Katz and Sarnak came up with the, Katz and Sarnak came up with looking at what's called the n-level density. And so the n-level density only depends on what's going on near the central point. And the way it's defined is as follows. So you take some nice function phi, which for simplicity, I will assume can be written as a product of Schwartz functions. And there's reasons why you may not want to assume it's a product. Nobody wants to hear technicalities like this. So we'll just assume it's a product. And I'm going to sum over distinct zeros. And by zeros, I mean none of the j's are plus or minus anything else. This just means I have to do some inclusion exclusion if I want to drop this and use the explicit formula. This leads to nicer calculations. And so much of the subject is trying to find which object can you combinatorially study and is going to have a nice limit. It turns out things work nicer like this. It's not a big deal. You can always reduce these to pure sums and just play inclusion exclusion. What's nice about this statistic is because the functions are Schwartz, the individual zeros contribute in the limit. Which zeros? The ones near the central point. In fact, the ones at the central point contribute the most, and the further up you go, the less contribution it has. Unfortunately, you can no longer look at just one L function. So now what you do is you put your L functions in a family, and then the hope is that if you average over a family, you can somehow execute these sums over the Fourier coefficients and get some results about average behavior. And so there's a whole slew of results, and the big conjecture is that the behavior of zeros of L functions are the same as behaviors of eigenvalues of a specific family of matrices. Which family of matrices? Looking at monodromy groups and function field analogs gives you an idea of which one to look at. We have some recipes that suggest what we should study. There's a lot of difficulty in proving this. The hope is that, as I said, if you average over and you take the limit, summing over the zeros should be the same as integrating your test function against some nice universal function, which depends only on the symmetry of what you're looking at. So just to link things so that you can talk to a physicist if you ever run into one of them, we talk about zeros, they talk about energy levels. They shoot neutrons in, we shoot a Schwartz test function. They can only shoot neutrons with a given energy band. To us, it's the support of the test function. We would love to use an arbitrary test function. If we could do that, we could take essentially approximations to the Dirac delta function and see what's going on at the central point and prove everything we want. We can't take a delta function because unfortunately the Fourier transform of the delta function is identically 1, which means we would have to do sums over all primes. We can't do that. You'll see very shortly when we look at Dirichlet L functions just how bad this is. And so this is why we can only get partial results because we can't shoot in what we want. And we have to do the best with what we can. All right, so the main tools in doing these is trying to control the conductor of the family. This is technical. The explicit formula, which we talked about from complex analysis. And then we need averaging formulas for the stuff that arises. So instead of going through the detailed calculations, we'll look for Dirichlet L functions. As a motivation as to why you might care about something like this, let's use this to bound the order vanishing at the central point. So if I take phi to be a non-negative function, then the average rank times phi of 0 would just be less than equal to this integral. And so if I just divide by phi of 0, I'm going to get a bound. And so with Chris Hughes years ago, we proved that there is some constant C of n that if you use the n level density, you get that the probability of having at least r zeros at the central point is decaying like 1 over r to the n. Unfortunately, the constant grows with n, so as n gets larger, the constant gets larger, and this only becomes useful as r gets larger with n. And so this is why you get stupid results such as at most 250% of the forms have 4 zeros at the central point. There's faster ways of proving that. But eventually, I start having, what if I have even more zeros? Then it becomes useful again. Okay, so I'm now going to shift and just go through a typical calculation for Dirichlet-L functions to give you a sense of how this is done. It's very misleading. It's not this nice in general. Again, I'm going to assume everybody has seen Dirichlet characters before, nice and multiplicative. There are m-2 primitive characters. And if I take m to the prime, I can write things down very explicitly. I can write things down in general. And so I can do all these calculations in great detail with my students without having to go into too much stuff. So it's a wonderful springboard to get to see more interesting stuff. And then we have lots of different normalizations. If I want to build the L function, it's going to satisfy a functional equation. There's going to be a sign of the functional equation. And we can start looking at the zeros. So we use the explicit formula to relate the sums over the scaled zeros to the sums over primes and prime squares. And I can look at different families and then just try to execute sums over all characters. If you don't want to do all characters, you could say, maybe I want to restrict to quadratic characters or cubic characters. And so the conductors might not be the same. And now if I'm looking at quadratic characters, these will all be 1. I expect to see a different family structure there than in the case of everything. So I only have to understand the sums over primes and prime squareds. And so how do I do this? Well, what's nice is all of the Dirichlet-L functions have the same character, have the same conductor. So I can do one of the only 2 things we learn in multivariable calculus. I can switch the order of summation. I can pass the sum over the characters through the test function, and then just execute the sum over the characters. Well, if we summed over all the characters, it's m-1 if k is 1 mod m and 0 otherwise. We don't have all the characters. We don't have the principal character. Well, it's not that bad. I subtract 1 because we don't have the principal character. And then we just feed this into the formula, and we're left with trying to understand sums like this. And so this is not that bad to do. And so we'll look at the first sum, the sum of 1 over p to the 1/2. And so I get 2 terms like this. And so the important thing to note is the second sum is over primes congruent to 1 mod m. And this is basically a coefficient of 1. This is basically a coefficient of -2 over m-2. So the coefficient here is much smaller, but the primes here are much less frequent. So these are basically of similar size, but opposite sign. And so I just now approximate by just say, I just bound everything. And then the first sum is of size p to the -1/2. The second is of size p to the -1/2. I do expect there to be cancellation. I'm not going to see that because I'm just being trivial. I don't really want to play log games. You don't want me to play log games. So I'm going to just replace the sums with sums over integers. But the important thing to note is the smallest prime congruent to 1 mod m is at least m+1. It can't be 1. And so that second sum has to start at m+1. And when I do that, I end up getting that the sum is bounded by 1 over m to the sigma over 2. So there's no contribution for support up to 2. If I wanted to get larger support, I would have to do a much better analysis of how are the primes distributed mod equal to 1 mod m, that one residue class. And so now this is related to some really fine questions about the distribution of primes in residue classes. And there should be some cancellation. I expect to be able to push this further. With any reasonable assumption, you can get support going all the way up to either -4,4 or -∞∞ if you assume some really strong things. This is just for completeness, putting up the second sum. Okay, the second sum was up there. So it's a very similar calculation to do the second sum. If you want to, I urge you to do it yourself, or just look at later. So Cuspidal new forms. This is where it's nice to have lots of students who can do long, involved, tedious calculations. And so the project here took several years and several summers to complete. And so there's a lot of results that are known for looking at families of cuspidal new forms. This was one of the first families studied by Katz-Sarnak, and they showed that the density agrees with that of SO even or SO odd matrices. And so they only looked at the 1-level density. And they got support up to -2, too. And then the question was, how far can we push this? And so the hope is we could get up to, for the n level, to 2 over n. And it took a long time before we were able to do that. There were a lot of obstructions and technical stuff that came up to play. I'm going to assume everybody has seen Cuspidal new forms. Again, this is just so if anybody ever downloads the slides, the explanations are here. The main thing is just how do we want to normalize things? It's always a game, so I will divide by the norm of my form, put in some gamma factors, put in some of the independents, and get some nice numbers, see. And then we need some kind of averaging formula, or this is going to be useful. And so we have the Peterson formula. This is the analog of the character formula we had for Dirichlet functions, where if I look at the sum of the product, I get this horrible mess involving the Klusterman function and the Bessel function. And that needs to be done. And so we then use the explicit formula to relate sums over zeros to sums over primes of the Fourier transform with the coefficients. And then the main result is Varnitz-Lewis-Sarnak in a masterful piece of analysis. We're able to figure out the resulting integral with sums and everything of the Bessel-Klusterman piece. So they were able to figure out what that is. Unfortunately, I'm going to skip all the technical details. Unfortunately, what we need to do, we have a two-dimensional analog. So one possibility is to try to look at a two-dimensional generalization of what Varnitz-Lewis-Sarnak did to handle something like that. The other option is to cheat. And I did give this to some students and just see, is there a way from first principles to try to generalize the argument? It became really bad. But there's a really nice change of variable you can do here. And so if I change variables, or just skip a slide. Oh, okay. So when the slide seems to have vanished, yeah, slide has vanished. Okay. So if I change variables, we had log of x1 over r1, log of x2 over log of r. Let's let u1 be x1, and let's let u2 be x1 over x1. Well, if I have the log of u2 over u1, that's the log of u2 minus the log of u1. Now I have the log of u1, and then phi at the log of u2 minus the log of u1. That's a convolution. So when you do this change of variables, I'm essentially replacing this with a convolution. Well, if I integrate that, I now get a new test function. And now I reduce to the Varnitz-Lewis-Sarnak result, where my test function now is a convolution of two test functions. And you can do this for higher levels as well. It just becomes an n-fold convolution. The problem is random matrix theory was expecting us to be honest and look at the calculations directly. And so combinatorially, this is not what random matrix theory was expecting. They were not expecting us to reduce it down to one-dimensional calculation. Now you have to expand it back up and show that things match. It turns out that there's a lot of challenges in making things match, enough that I was able to give students projects for several years before we finally got all the pieces to work, and we were able to get it to work up to -2,2. So now an application of this is to try to get better results about bounding at the central point. How many zeros do we have? How far do we have to go before we see more zeros? There are three main goals or three main approaches you can take. One is you can try to increase the support either for the one level or the n level. For the most part, we've basically hit the wall on that. And it's extremely hard to increase the support. Another is we can try to optimize the test function. Can we find a better function phi to use? And the third is to use the n level densities. And so what I want to do is I want to give you a sense of the benefits of each approach and highlight how students can get involved in all this stuff, and talk a little bit about what some of my students are going to be looking at this summer. So there's a lot of papers talking about increasing support and optimizing the test function. Increasing support is very hard. Optimizing the test function turns out not to give that much. Just naive approximations do almost as good as pages and pages of advanced functional analysis. And so I'm going to talk about some work I've done actually with some high school students on trying to get better results for bounding at the central point. And so the naive test function, and this was related to some of the jokes I was doing earlier today, is sine squared of x over x squared. And then just adjusting it a little bit, because you should always have a factor of pi somewhere, and then you want to adjust what the support is, so you put in this extra factor of Vn. And then we can look at the Fourier transform of that. So this is a really convenient pair to work with. It's easy to do the resulting calculations, and it's almost as good as what you would get. The optimal, just for completeness, Jeff Vanderkam worked this out many years ago. It gives slightly better results. There are methods to do this. The larger the support is, the harder it is to explicitly write down what the optimal test function is. We only know the optimal test function up to certain levels of support. So if we wanted to calculate, say, the bound for the one level, well, I have my scaled zeros. And so near the central point, the zero should be spaced approximately 1 over log of the conductor. So I'm rescaling by the log of conductor, so I have mean spacing 1. I sum over all the zeros. I then sum over all the forms in the family, and I divide by the number of forms in the family. And so this should give me the average. And if I take my function phi to be non-negative, then if I drop everything but what's going on at the central point, I've only thrown away a positive thing. So what this equals in the limit will then be an upper bound, and I can use this to bound the order vanishing. And this is where you get the result that the probability of having at least R zeros is 1 over R times some nice quantity. The quantity makes sense. You have to divide by 1 over phi of 0, because when I plug in 0, I'm going to get phi of 0 here. If I just rescale phi by dividing by 100, I shouldn't be changing my bound. So this should be some nice scaling like this. All right, so this is what you get if you look at the one level. And so here are results. And I debated doing this all the time. I'm only doing this once. I'm going to put them on the same slide. And you can see how much of a gain you get by going from the naive test function to the optimal test function. If you can get an improvement, sure, get an improvement. But the amount you're gaining by is negligible. All right, looking at the one level, the two level, and the fourth centered moment, it's not quite the n-level density. It's a close cousin. Really doesn't matter which one you look at. You can see that looking at the higher moments gives you a much better result. So if I wanted to calculate something absurd like the probability of having 50 zeros at the central point, I don't really expect that to be happening. I'm getting a small number 0.017, but if I'm using the fourth centered moment, I'm getting something else like 7 times 10 to the negative 8. I still expect in the limit that the answer is 0, so the results are too high. It becomes an interesting game to ask, as I increase the moment, how much faster is this going to increase? What can we say? When do things kick in? The big ingredient is to have as good of a support as possible. And this was the project. It was only finally accepted maybe about a month ago. This was done with many students over the years, where we were able to show for support up to 2 over n for the n-level density. This is what you get. All that matters is it's something that's known. You tell me what phi is, and we can do this. Not necessarily in closed form, unfortunately, but we can at least numerically approximate it to whatever precision we want for finite value of n, and we can get values for this. And then we can use that to get results. So how would we get results? So, we look at the sum over zeros, and I'm looking at the centered moments. It's a little bit easier, so I'm subtracting off the mean, and I'm dividing by n. And I know everybody's looking very carefully, and notice that I'm not dividing by the n by looking at just a finite level approximation. I'm looking at the scaling limit for the mean. And the reason is, with a little bit of approximation and whatnot, you can show that the convergence is fast enough that I can replace the mean at a finite level with the limiting value and just control how much the error is. It's not going to matter in the limit. And so we know what the mean is. We look at the sum, we raise it to the nth power. If n is even, if we drop any terms, we're just dropping positive numbers, and we're going to get an upper bound. And so we end up getting nice results like this. For an even n, we can bound what is the probability you have at least R zeros at the central point. It only works if R is greater than or equal to the mean. And that's because if we look at cases where we have fewer than this number of zeros at the central point, we're going to have some troubles just in substituting there. So these results only kick in if you go down a little bit. And so the proof isn't too bad. So what we do is we write what's going on is we have R zeros at the central point, then we have the contribution for all the other zeros, and then we have the mean that we're subtracting off, and then we raise it to the nth power. And I'm throwing away all the forms that don't have at least R zeros at the central point. Because n is even, that's going to be a positive, it's going to be a non-negative number. And so my bound will still be fine. I can throw those away and restrict myself to forms with at least R zeros at the central point. Because I'm assuming R phi of 0 is greater than the mean, I can drop the B of phi term. And I'm not in a situation where if I had that number, I might have made it smaller. I mean, I might have made it larger because it's a negative number. And this is you have to be careful of. -1 is larger than -2, even though 2 is larger than 1. How many people know about the Wendy's incident? I heard that a lot of people did not buy. Okay, you've heard this?
I've heard of it.
That people wouldn't get the 3rd pounder at Wendy's because why would I pay the same amount as a 1/4 pounder that I could get elsewhere for a 1/3 of a pounder? So always be careful. You've heard this? No, okay. Always be careful with basic algebra. So we've got to be a little bit careful like that. It's not too bad. We get nice results. And then when we look at this, here are the results we get looking at support up to 2/n using the various levels. I'll just focus on one number. If I want to look at 20 zeros at the central point using the one level, it's 0.0437, and I'm using the naive test function. And then if I use the optimal test function, it's 0.0432. So essentially, not much of a difference is coming by using the optimal versus the naive. The real benefit is using and being able to use the n-level density. Okay, you can then ask, for given order vanishing at the central point, what n is the best n to use? There's lots of games you can play like this, lots of problems you can spin off for students. I'm going to skip the rest on that. And for the last about, I think about 7-8 minutes, I want to talk about the last thing, trying to bound how far do you have to go to find the smallest zero above the central point in various families. And so, since it's the end of the talk now, we can now assume GRH. A lot of the calculations we've been doing before actually do not need GRH. You can do a lot of these calculations without GRH. But at this point, let's assume GRH. And let's try to ask, how far do we have to go before we see the first zero above the central point? And this is always going to be relative to the average spacing. Because if we expect it to be of size 1/log of conductor, well, as the conductor gets larger, it's going to get closer to the zero, it's going to get closer to the central point, so the zero is going to get lower. So I want to know how likely are you to get a zero that's really small relative to the correct scale to look at. And so a result I wish I had, but at least it was kept in the Miller family of Sarnak students, Stephen David Miller, showed that for certain types of L functions, the first zero is going to be at most 14.13. For more general L functions, it was shown it's at most 22.661. But again, as the conductor gets larger, you're going to be much, much smaller than this. And so the question is, how far do you have to go? Mester showed for elliptic curves, the first zero is at most on the order of 1/log conductor. Again, very far from what we hope. With another one of my undergrads years ago, we looked at families of elliptic curves that had geometric rank R, and we were able to show if you go up to some nice multiple of 1/sigma, where sigma is the largest support you can do, you will see at least that many zeros. It's nice, but it's also in some sense really bad because we expect that, well, if it has geometric rank R, Birch-Swinnerton is true, so you don't need to go anywhere. And the smaller sigma is, the less support you have, the worse the result is. And for elliptic curves, the support is very bad. So we have to go a decent distance away before we're guaranteed to see the zeros that we know must be there because we believe Birch-Swinnerton. What I have done with some of my students recently is trying to look at how far do we have to go to see the lowest first zero in a family of cuspidal new forms. So in all of them, what is the smallest that first zero can be? And so what we were able to do is, interestingly, now we're going to be letting our exponent be odd, not even. We showed that if you can find a test function phi, which is non-negative and non-increasing, for x less than omega, and it's non-positive for x greater than omega, then we have a certain inequality, and there will be at least one form with at least one normalized zero in minus omega omega. And the way we're going to construct such a function that has these properties where it's non-increasing, it's non-negative up to omega, and it's non-positive beyond. This is so that when we look at the contribution of zeros, anything up to omega, you only make the contribution large if you push them all the way up to zero. and anything beyond is going to be a negative contribution, which is going to make things smaller. So if I drop it, it makes things larger. That's the whole reason to have something like this. We get a similar percentages. I had mentioned earlier that some of my results are bad. 420%, obviously absurd, but eventually the results get better in terms of bounding. How often do we have at least, say, 34 zeros in an interval about 0.8 of the average spacing? Well, if the average spacing is 1, 0.8 last time I checked, which was this morning when I was practicing, is less than 1. So I don't really expect there to be that many zeros less than 0.8 of the average spacing. So having 34 zeros is quite a lot in the window of 0.8. And so a bound of 3% is quite bad. But a bound of 10 to the negative 6, that's not reasonable. So it does eventually, by looking at the higher levels, it does start to give you really good results. So for the last 4 minutes or so, let me quickly show you how you prove this. So we start with the convolution. So I need to find a function that has desired properties. This is where there is a lot of opportunity for students to improve. This is a procedure that will construct such phi. If you know the method of divine inspiration, if you can just write down a better phi, I don't care where it came from, we can use it. But to find a phi that has the desired properties, this is the only construction we know, and this is generalizing work by Mester and others. If you convolve A with itself, and we've seen convolutions earlier, the Fourier transform of a convolution is the product of the Fourier transforms. So if you convolve A with itself, it's non-negative. And this is a great way to get a non-negative, to get a function whose Fourier transform is non-negative. Convolve a function with itself, take the Fourier transform. Okay. Next thing to do is, so I take some nice function h, I rescale it involving the support, I can do things, that's the sigma. I convolve f with itself, I take the Fourier transform, and that's going to give me a function that's non-negative. And now I take some derivatives, because the Fourier transform of the derivative is a multiplication. So if I take two derivatives, I'm going to essentially be multiplying it by x squared. And this is now set up, so I take g hat, which is non-negative, and I multiply by 1 minus x over omega squared. Oh, great. This factor is positive up to omega and negative beyond. And so this is going to give me exactly what I need. And so then we play a game, very similar as before. We replace the mean and the limit, all this stuff exactly as before. And we want to be able to drop things because n is odd. If I have something that's negative and I throw it away, I'm only going to be making things bigger. And that's why I want n to be odd now, so I can just reduce to what's going on. And if I move all the zeros before omega to 0, I haven't made things smaller. And that's going to lead to my upper bounds. And so, the calculation is very similar. So I'm going to skip the calculation. And so at the end of the day, we get that our function phi omega has to satisfy certain inequalities. As long as we can find such a function, it works. And so, I don't know what happened. I guess I downloaded the wrong slide. I apologize. What you would have seen is it's a little bit less than a quarter if you use the function we got here. So a little bit less than a quarter. I then had some students who worked a little bit harder. And instead of looking at just something involving a quadratic term, they went all the way up to the sextic term. And it was ever so slightly larger, like the fourth decimal place, third decimal place, something like that. And so the gain you get from going into a more involved space, looking at up to 6 derivatives, was extremely minimal. So one of the projects I'm going to give students is, can you try to estimate how much of a gain would we get if we keep adding more and more derivatives? I think it's going to be extremely small. We need to find a better space of functions to look at. So if anybody knows people who know functional analysis, there's a lot that could be done with a project like this, where we just need ways to search for the various spaces. So we'll be trying to optimize the test function, looking at different spaces and seeing how much we can gain. Increasing the support is going to be too hard. What we did right now is we proved about bounds for just 1 0 in that interval. Well, just 1 0 is going to be a negligible contribution. So without too much work, we should be able to get some decent percentage of zeros have to be in this form, or it's not going to be enough to contribute in the limit. So there'll be some other results like that coming in the very near future. And then I'll just end with some references if people want to read further. So thank you. I did keep it under 45.
Any questions?
Yes.
So at the start with the motivation,
Yes. Yes. And I spent 2 summers doing that.
You said that the motivation was that we have this, Schrodinger's equation.
Yes.
We don't know the Hamiltonian. And so we can just model it with a random matrix.
Yes.
I feel like the same question comes up here. Let's say that you wanted to study analytic ranks of elliptic curves. Elliptic curves are a very small part of the family of Cuspidal
Yes.
So what insight, if any, does this shed on, like, should we expect that elliptic curve L functions behave the same as the average member of this family?
I mean, this is a great question. I like to phrase it as we're looking for fat, thin families. The family has to be fat enough that we have averaging formulas at our disposal, but thin enough so that we can see different types of behavior.
Right.
And so elliptic curves do have averaging formulas available, but they're not as good as the averaging formulas for all cuspidal new forms. So we don't have anything as good as the Peterson formula. And this is why, the support for elliptic curves is much worse.
Right.
But we know, but we know there's also structure to the elliptic curves.
I'm not asking what we can improve. I'm asking what should we expect.
I would say we should probably expect modulo the forced zeros at the central point. Everything else should be behaving similarly.
Okay.
I do have some results with students where, when we were trying to model zeros near the central point, one of the big issues with elliptic curve L functions is the discretization of the L function at the central point. And this is something that's true for all cuspidal new forms. The higher the weight, the less the discretization is. And we actually see that there's much less impact looking at weight 4 than looking at weight 2. And so I think elliptic curves and weight 2 cusp forms will have slightly different behavior in what's going on near the central point because of the discretization effect. I think that does have some impact. But in terms of just what's going to happen, in general, a lot of these models is the main term is governed by this universal behavior. And the lower order terms, the rate of convergence, depend on structure of the system you're looking at. And I have, a paper from early in my career where I look at various families of elliptic curves that have different structure. And you can try to see how does the torsion structure or how does something like that impact the rate of convergence. And you can see some of that coming into play.
Yeah, this is really beautiful. So thanks for this. I wanted to ask you kind of a meta question.
Yes.
About all of this. A lot of us who work with undergrads have to have this balance of having them to know the theory, having them to prove something, but then also maybe have them to do more computational work. And it seems like in a lot of this, you have students doing a little bit of.
And so this is something I picked up from David Farmer when I worked with him at AIM years ago, is basically on day one, try to have the students doing something. So they're not just reading papers. And so for a lot of this, I'll often have them prove special cases or generalizations just so that they start very quickly doing something. So when they're reading a paper, they're then trying to generalize it in another case. And this is being recorded, so I will not have the equipment malfunction. So the case that they may be generalizing, nobody may have a huge desire to see it done. But it's a really good exercise for them to do it. And this way they can build up the techniques and they at least get something out of it. They get a paper and they really understand all of the details. If it's possible for them to do some computations, they start getting a sense of how do you do these computations efficiently. They start learning how to use the parallel computing available for some of these problems that our school has. And then when they get to the real stuff, the challenge is, what do they assume as a black box? What do they assume that, okay, when I get to grad school, we'll see this. They don't need to see a proof of the Peterson formula. Once we know that this expansion exists, you can just, it's like a highway entrance ramp. You can just come onto the problem there and trust that people have done a good job to get you to this point. And I think this is something we all struggle with, is how much of the time do we want them learning the theory? And the danger is always, well, what if the theory is wrong? I'm pretty confident that we've got the Kuznetsov trace formula down correct by now. I'm pretty confident on the Peterson formula. But I have found books with typos. I found one paper that had the Kuznetsov trace formula where one of the terms was the integral of an odd function over a symmetric region. That's 0. Yeah, I'm pretty sure they didn't mean to include a term that was identically 0. I think they dropped a factor of x in the integral, and it's supposed to be an even integral. And so we then had to double check with another book. Yes, this is a real danger. I'd be curious during breaks to hear what other people do in such situations.